Good morning to everyone. So today we are going to see about information theory and coding in chapter unit 1, Huffman coding and Shannon-Fenno coding. So here we are going to see first the need for coding. Okay, why we go for the coding techniques. Okay, so the primary need of the coding technique is normally we are sending the information from sender to receiver. Okay, so during this process, the information signal or the data should have the necessary properties. So then only we have to send the information from the one place to another place. So this data should have some necessary properties. Okay. So hence there are some information coding techniques used to transform the message signal to transferable signal. Okay. It is a transferred signal through the transmission channel. Okay. So here two of the coding channels are here we preferred. The first one is Huffman coding. Okay. Huffman coding and Shannon-Fenno coding. First one, Huffman coding. So here, what is the difference between the Shannon-Fenno coding and Huffman coding? Why we prefer Shannon-Fenno coding and why we prefer the Huffman coding? So the most difference between the Huffman coding and Shannon-Fenno coding is the Huffman coding provides variable length coding. So the length is different; it is variable. So while the Shannon-Fenno coding provides a limited length of encoding. Okay. So this algorithm, that means the Huffman coding assigns a different number of binary digits to the messages according to their probabilities of occurrence. So this will give a different number of binary digits to the messages. Okay. So the Huffman coding also uses the same principle in Shannon-Fenno coding, but this type of coding makes average number of binary digits per message. Okay. Nearly it is equal to entropy. So normally we called the entropy is average number of bits per message. Okay. So this is also using the same principle. Okay. So the definition of the Huffman coding is it is a compression techniques that handles the data compression in ASCII code characters developed by the David Huffman in 1952. So the Huffman coding is the compression algorithm that is based on the top-down process. Okay, so it is developed by David Huffman in 1952. So that's why this code is called Huffman coding. Okay. So this coding is a lossless data compression algorithm. So already we know what is lossless compression means. During the process in compression techniques, we need to send the original information sent by the receiver to the sent by the sender to receiver. So during this process, we don't need any loss, okay, in compression technique. So this is called lossless data compression that assigns the variable length binary codes to characters. It is based on the frequencies. Okay. So normally it is a no code is a prefix of another, but it is eliminating the ambiguity during the decoding. Okay. So this technique is widely used in data compression format GZIP and JPEG and MB3. So these are the applications of the Huffman coding. Then before we are going to solve the problems, first we know what are the steps involved in the Huffman coding. Okay. So the first step is, for example, the total number of source symbols are 8 symbols. Okay. So first step, we are going to arrange the source symbols in the decreasing order of probability. Okay. So the first step is the source symbols are arranged in an order of decreasing probabilities. That means, for example, totally 8 symbols, each symbol having a different probabilities. Okay. So we can arrange the probabilities in the decreasing manner. Okay. In the descending order. Okay. So then the two symbols, the second step is both symbols. For example, then two symbols of low probability are combined. Okay. So decreasing order means the last two symbols we can combine and assign. The uppermost group is 0 and the lowermost one is 1. Okay. So totally we have 8 symbols. The first step, we need to arrange the symbols in the decreasing order. So the lowest probability in the last two symbols. Okay. So these last two symbols are combined and we can assign the uppermost one is 0 and lowermost one is 1. So this is the second step. Okay. Then the next one is, then the combined last two probabilities are moved to the next stage. Okay. So the next stage also the same principle. We have to arrange the symbols in the decreasing order or descending order. Okay. But suppose the first group, the last probability, that combined probability, the total is highest means we need to arrange in the second stage also in the decreasing manner. Okay. So this is the third step. So then the combined last two probabilities are moved to next stage, and next stage again the symbols are arranged in a decreasing probability. So this is the third step. Okay. Then the next one is, again the two symbols in the last two probabilities are combined in the second stage. So second stage, first arrange in a decreasing order. Again we can repeat the same step. The two symbols in the last low probabilities are combined, and uppermost one is 0 and lowermost one is 1. Okay. So this is the fourth step. Okay. So then again fifth one, repeat the above steps, the same steps until only two those symbols are left. Okay. And assign the uppermost one is 0 and lowermost one is 1. Okay. So once the two symbols only left now, we can stop the process. Okay. Until we can during the same steps in the above. Okay. So this is the steps involved in the Huffman coding. So we can, once again, we can summarize. The first step is that source symbols are arranged in the decreasing manner. After that, we can combine the last low probabilities two symbols. Then we can assign the uppermost one is 0 and lowermost one is 1. Then after that, these two probabilities are moved to the next stage. In next stage also the same process repeated. We can arrange the source symbols in a decreasing order. Okay. After that, we can again move the last two symbols into the next stage. Okay. So these steps are again the repeat the above steps until two most symbols only left in the stage. Okay, next stage. So the finally the last two symbols are assigned. The uppermost one is 0 and lowermost one is 1. So this is the steps. Okay. So now we are moving to the example 1 in Huffman coding. Here you see that the totally we have 5 symbols: S4, S0, S1, S2, S3 and S4. So totally 5 symbols. The corresponding probabilities of each symbol S0 is 0.4, S1 is 0.2, S2 is 0.2 and S3 is 0.1 and S4 is 0.1. Okay. So I already told what are the steps involved in Huffman coding. The first step is we are arranging the symbols with their probabilities in the decreasing order or descending order. Okay. So here in the first stage 1, here we can arrange the symbols in the decreasing order. See that it is in decreasing order only. 0.4 is the highest probability and 0.2 then 0.1. Okay. Then the next step is combine the least last two probabilities. So the last two probabilities have the least probability, low probability, and combine these two. Then assign the uppermost one is 0 and lowermost one is 1. Okay. So then we move this probability to the next stage. Okay. The next stage is add these two probabilities. It is 0.1 plus 0.2. So this 0.2 is moved to the next stage 2. Okay. So the same steps when the followed in the stage 2 also. We are arranging the probabilities in the descending order. Suppose the stage 1, this combined probabilities higher one, we will move to here only. So 0.4, then 0.2, then 0.2, again 0.2. Okay. Then again repeat the same step. The last two probabilities are combined and assign the uppermost one is 0 and lowermost one is 1. Okay. Then again combine these two probabilities and move to stage 3. Okay, here see that it is 0.4, 0.2 plus 0.4, the last two probabilities, the total is 0.4. So, okay, so here we move to stage 3 in first 0.4. So here this is also first, okay, can have 0.4, then 0.4, then 0.2. Okay, so in stage 3 also arrange the probabilities in the decreasing order. Then again we combined the last two probabilities, the 0.4 and 0.2, and assign upper one is 0, the lower one is 1. Okay, then add these two probabilities. So the total is 0.4 plus 0.2, it is 0.6. Okay, so in stage 4 it comes first. Okay, because the highermost one is 0.6, so it comes first, then the second one is 0.4. Okay, then in stage 4 only we have two probabilities, and stop the process and assign the uppermost one is 0 and lowermost one is 1. Okay, so this is the process, and this is the code tree of Huffman code tree. Then we can trace the code word for the first stage, symbol 1 and 2, 3, 4, 5. Okay, so the first symbol is S0. So it is here you can trace according this. So first it come in stage 2, then it go down. So it is a 0. Then again it goes to up. Okay, so 0, 0 is the probability. So see this figure. Okay, the tracing is clearly. Okay, so here the symbol 1, 0.4, 0.4. So it is the symbol 1 is, it is 0 and 0. Then S2 is here, it come here, the down. Then the code word is 0. Then it goes to here. Then here it is 1. So 0, 1. Okay. So we can write it is 1, 0, 1. But here the MSB is first and the LSB is next. So we can change the code words 1, 0. Okay. Then S3 is, it is 0, 1. Then it goes to here 1, 1. So the 1, 1. So once you change the code word means 1, 1 is 1, 1 only. Okay. Then the next one is S4 is, here it is 0, then it is 1, then it is 0. Okay, 0, 1, 0. So 0, 1, 0, you change or rearrange the words, it is 0, 1, 0 only. Okay. Then S5 is, here it is 1, then it goes to here, and here it is 1, then here it is 0. So 1, 1, 0. Then we change the MSB and LSB, then it is 0, 1, 1. So then calculate the number of bits in the code word. The S1 is 0, 0, so only 2 bits. Here also 2 bits. This is also 2 bits. Then S4 is 3 bits. S5 is 3 bits. Okay. Then after that, we can calculate the entropy of the source. So the entropy is, formula is H, represented as H. H, it is equal to summation of Pi and log summation of Pi log 1 by Pi to the base 2. Okay. So we can calculate the entropy here. The Pi represents the first symbol. Here I represent 1 to the 5 symbols. Okay. So here the first symbol probability is 0.4. So log 1 by 0.4 to the base 2 plus the second probability of S2 is 0.2. So here S2 and S3 has same probability 0.2. So we can multiply into 2 into 0.2 into log 1 by 0.2 to the base 2. Plus again the last two symbols have same probability. It is 0.1. So 2 into 0.1 log 1 by 0.1 to the base 2. Okay. So here the log 1 by 0.4 to the base 2, it is not available. We are not able to calculate through the calculator. So we can convert a log to the base 2 into log to the base 10. Okay. So we can easily calculate. So log 2 to the base log 1 by 0.4 to the base 2, it is converted into log 1 by 0.4 to the base 10 divided by log 2 to the base 10. So using this formula, we can calculate the log to the base 2. Okay, so once again I will tell you, it is log 1 by 0.4 to the base 2 is converted into log 1 by 0.4 to the base 10 divided by log 2 to the base 10. Okay, then we calculate this equation, then we can get 2.1216 bits per symbol. So this is the entropy of the symbol. Okay. Then we can calculate the average code word length. Okay, so the average code word length, L average, L it is equal to summation of Pi and Ni. So this Pi is probability and Ni is number of bits in the code word. Okay, so here it is equal to 2 into 0.4. So 2 into 0.4 means this is the code word length 2 and the probability of symbol S1 is 0.4. Okay, so 2 into 0.4 plus 2 into here 2 times the 0.2, the probability into the code word length 2. Okay, plus 3 into the code word length, it is 3 into the probability is 0.1 into 2 times. Okay, so into 2 because the last two symbols S4 and S5 have 0.1 probability. So 0.1 into 2. So we can get it is 2.2 bits per symbol. This is the average length of the code word. Okay. Then after that we can calculate the efficiency. Then efficiency it is equal to h by L log gamma, it is divided by to the base 2. Okay. Or otherwise h average information entropy divided by average code word length L. Okay. So it is equal to 2. So already we calculated the entropy 2.1216 divided by it is 2.2 into log 2 to the base 2. So it is equal to 96.4. Okay. So this is the efficiency of the symbols. So finally we have calculated the efficiency of the source symbols. Then the example 2. So see this example 2. So here totally, we have 6 symbols, x1, x2, x3, x4, x5, x6. So here also the same process. In the first step, we are arranging the probabilities in the decreasing order. It is the highermost one is 0.3, then 0.25, 0.2, 0.12, and 0.08 and 0.05. Okay. Then again, we combined the least two probabilities and assign uppermost one is 0 and the lowermost one is 1. Okay, then add these two probability, then it is moved to the second stage. So the total of this 0.08 plus 0.05 is 0.13. Okay, so this move to the last in the stage 2. Okay, in stage 2 also we can arrange the probability in the decreasing order, then combine the last two probabilities and assign uppermost one is 0 and lowermost one is 1. So we can repeat the step in the stage 5 up to stage 5. Here in stage 5, only two probabilities and we can assign the upper one is 0 and lower one is 1. Okay. Then finally, we can trace the code words. So here see that the code word of x1 symbol is, it is 0 and 0. So likewise, we can trace here 0 and 0. Okay. In x2 symbol is, so here it first come down, it is 1. Then it goes to up, it is 0. So the code word for x2 is 1, then 0. Okay. Then code word of x3 is, it is 1, then it is 1. So 1, 1. Then code word of x4 is 1, then 0. So 1, 0. Then again it is 1. So 1, 0, 1. Then x4 is, it is 1, then 0, then it is 1. So 1, 0, 1. x5 is, it is 0, then it is 0, then 0, then it is 1. So 0, 0, 0, 1. So we can exchange the MSB and LSB. So it is 1, 0, 0, 0. Okay. Then x5, 6 is, it is 1, then 0, 1, 0, then 0, 1, 0, 0, then 1. So 1, 0, 0, 1. So this is the code word for x6. Then after that, we can calculate the entropy and the efficiency of the source. Okay. Then here, the example 3, so here it has 5 symbols, 6 symbols, A0, A1, 2, 3, 4, 5. Okay. So here also the same principle, 0 0.4, 0 0.3, 0 0.2, 0.4, 0.04, 0.04 and 0.02. So the same steps are repeated up to the last one. Okay. Then trace the code word for the symbols. So the A0 got it is 1 code word, A1 is 00. A2 is 0, 1, 0, A3 is 0, 1, 1, 1, then A4 is 0, 1, 1, 0, 0, then A5 is 0, 1, 1, 0, 1, 1. Okay. The average code word length of this source is, it is 2.06 binary digits per symbol, and the entropy of the source is 1.999. So the entropy is calculated by the formula. It is H, it is equal to summation of 1 by pi to the base 2. Okay, then average code word length is calculated in the formula of summation of it is pi and ni. Pi represents the probability of the each symbol, and ni is the number of digits in the code word in each symbol. Okay. Then move to Shannon-Fano coding. So here in Shannon-Fano coding also, it is a compression algorithm or encoding algorithm. It is used to generate the uniquely decodable code. It's a unique code. Okay. It was developed by the Shannon and Robert Fano in 1949. So it is called Shannon-Fano coding. Okay. Then it is developed earlier than the Huffman coding technique. But it is similar to Huffman coding. The Shannon-Fano coding also uses the probabilities of the data for encoding. So this algorithm does not ensure the optimal code generation. Okay, so this coding is uses cumulative distribution function. So what are the steps involved in Shannon-Fano coding? So here the first step is source symbols are listed in order to decreasing order of the probabilities. The same step in the Huffman coding. Okay. So in already we told the Huffman coding, the first step is arrange the probabilities in the decreasing order. This is the first step. The same step repeated in the Shannon-Fano coding also. So after that, the second step is the total number of symbol is divided into two groups. Okay, the list is divided into two groups, and but the total probability of each group is nearly equal. Okay, so the condition is the probability of each group, the total probability of each group is almost equal. Okay, so this is the condition. So this is the second step. Then next one, each symbol in the first group receives 0. That means the uppermost group is, we can assign it as a 0, and the lowermost group we can assign it as 1. Okay. Then the next step is repeat the same above steps until two symbols are remaining or left. Okay. Then again, these two symbols, the uppermost symbol is assigned to 1 and the lower one is assigned to 1. 0. Upper one is assigned to 0 and lower one is 1. Okay. So this is also the same in the Huffman coding. Okay. So once more we can summarize. The first step is arrange the probabilities in the decreasing order or descending order. Then the next step is the total number of symbols are divided into two groups. Okay. But the condition is the total probability of each group is nearly equal. Then we can assign the uppermost group is 0 and the lower one is 1. Then repeat the above steps until two more symbols are left in the group. Okay. Again, we can assign the last two symbols. The first upper one is 0, the lower one is 1. Okay. Then after that, trace the code word and find the entropy and code efficiency and redundancy. Okay. So these are the steps involved in the Shannon-Fano coding. Now we are moving to the examples. Okay. The example 1. So here apply the Shannon-Fano coding for the following message or source. Okay. So here symbols are x1, x2, x3, x4, x5, x6. Okay. Totally 6 symbols and corresponding probabilities are 0.30, 0.25, 0.15 and 0.12, 0.08 and 0.10. Okay. So this is the problem. Okay. Then what is the solution means here? totally 6 symbols. We can arrange these symbols with their probabilities in the decreasing order. Okay, so here the first step, arranging the probabilities in a decreasing order. The highest one is 0.3, then 0.25, then 0.15, then 0.12, then it is a 0.10, then the last one is 0.08. Okay, the first step over. Then move to the second step. Second step is the total number of symbols divided into two groups, but the total probability of each group is nearly equal. Okay, so we can here divided the x1 and x2 are two groups, one group, and x3, x4, x6, x5 are the another group. Okay, so here you can calculate it is total probability of the first group is 0.30 plus 0.25, it is nearly 0.55. Okay, so this is also you can add the x3, x4, x6 and x5, it is nearly equal to it is 0.5. Okay, so almost it is equal. So we can separate the symbols into two groups. X1, X2 are one group, X3, X4, X6, X5 are another group. Okay. Then the next step is we can assign the uppermost group. So this group is 0. The lower one is 1. Okay. You can assign each symbol, it is 1. Okay. So 0, 0, 1, 1, 1, 1. Okay. Then next stage also we can repeat the same step. Divide the group in total number of symbols into two. So here we can two groups. First concentrate the first group. Okay. First group have only two symbols. We can separate or divide it into two groups and assign the upper one is 0 and lower one is 1. Okay. Then move to the second group. The second group have four symbols. So here we can divide it into two. Okay. X3 and X4 are one group and X6 and X5 are one group. Then assign the upper one is 0, 0 and the lower one is 1 and 1. Okay. Then move to stage 3. So here only one symbol is left. So leave it. And here X2 also only one symbol. So you can leave it. Then come to the third one, the X3 and X4. The third one, the two symbols are there. So we need to divide it into it is 2. So and then assign upper one is 0 and lower one is 1. Okay. Then move to the last one. Here also two symbols are there. So we need to divide this into 2 and assign the upper one is 0 and lower one is 1. Okay. Now see that in each one it is only one symbol in the group. So here 1, this is also 1, 1. Here also 1, here also only one symbol. The last also only 1. Okay. Then after that we can trace the code word. So here it is 0, 0. So 0, 0. Here it is 0, 1. Then 1, 0, 0. Then x4 is 1, 0, 1. X6 is 1, 1, 0. X5 is 1, 1, 1. So the last one. Then calculate that number of bits in the code word. The first X1 is number of bits 2, only 2 bits. Here also 2 bits. Here 3 bits, 1, 2, 3, 3 bits. 3 bits up to the last one is 3 bits. Okay. Then after that we can calculate the entropy. The formula is summation of I is equal to 1 to 6 because here totally 6 symbols and pi into xi. Okay, pi is probability. So here first we put the first probability of x1 is 0.3 into log 1 by 0.3 to the base 2. You can calculate with the log to the base 10 calculation I already told. Okay. So finally we got 2.418 bits for entropy or average information. Okay. Then calculate the length of the average length of the code word. So it is summation of I is equal to 1 to 6 pi into length. So pi is probability, it is 0.30 into length is 2. Then 0.25 into it is the 2. Then 0.15 into 3. Then 0.12 into 3 plus 0.10 into 3 plus 0.08 into 3. So finally we got 2.45 bits. Then calculate the efficiency. So efficiency, it is entropy divided by average length of the code word. Okay, entropy is H. It represented as H of X. So it is equal to, already we calculated, it is 2.418 bits. So 2.418 divided by 2.45. Then it is equal to 0.9869. So nearly it is 98%. It is efficiency. Then what is the redundancy? The formula is 1 minus eta. It is efficiency. So 1 minus 0.9869, it is equal to nearly 0.01. This is the redundancy of the source. Then the next example is x1 up to here totally we have 8 symbols. Okay, the same process repeated. The total number of probabilities are arranged in a decreasing order. Then we can separate these into two groups. Almost the probability, total probability of each group is equal to one, equal to nearly equal, and then approximately equal. Then assign the uppermost group is 0, 0. The lower one is 1, 1, 1. Okay. The same step repeated until that only two symbols are left. After that, trace the code word and find the average length of that means average number of bits in the code word. Then find the entropy and efficiency. Okay. So this is another one example. Here totally 6 symbols are there. The probabilities are 0.36, 0.18, 0.18, 0.12, 0.09 and 0.07. So this is already arranged in a decreasing order. Here also first two are in one group. It is divided into two groups. The first A1 and A2 are first group. A3, A4, A5, A6 are in the second group. Assign it is 0, it is 1. Okay. Then again it is divided into two groups. So the same steps are repeated. Then find the code word and finally calculate the efficiency and redundancy. Okay. In example 2 here it is a different because already we know the probabilities in the fraction. Okay, number. It is only 0.1, 0.4 likewise. So here it is in fraction. Find the code word in the probability of 1 by 4, 1 by 4, 1 by 8, 1 by 8, 1 by 16, 1 by 16 and 1 by 16 and 1 by 16. Okay. So totally 8 symbols. First two symbols are 1 by 4 and second two symbol probabilities are 1 by 8 and last four symbol probabilities are 1 by 16. Okay. So here first the step is arranging the probabilities in the decreasing order. So the highermost one is it is 1 by 4. So first we can put 1 by 4, 1 by 4, then 1 by 8, 1 by 8, then the last 1 by 16 up to 1 by 16. Okay. Then divided this into two groups. The first two symbols are one group. Then S3 to S8 are another group. Assign it as 0, it is 1. Okay. Then again the steps are repeated until the two more symbols are left. Then trace the code word. Here it is 0, 0. Then S2 is 0 and 1. S3 is here 1, 0, 0. Then S4 is 1, 0, 1. Then S5 is 1, 1, 0, 0. Then S6 is 1, 1, 0, 1. S7 is 1, 1, 1, 0. Then S8 is it is 1, 1, 1, 0. Okay. So here then calculate the length of the bits, number of bits in the code word, then calculate entropy and redundancy. So here the entropy H it is equal to summation of Pi log 1 by Pi to the base 2. So here the first probability is 1 by 4. So 2 into, because 2 means here two symbols have the same probability 1 by 4. So 2 into 1 by 4 into log 4 to the base 2 because log 4 means here 1 by 1 by 4. So the denominator comes to here numerator. So log 4 to the base 2. The finally calculate the equations. We got 2.75 bits. And the length of the code word, average length of the code word also, it is summation of Pi into Ni. So it is 2 because two symbols have same probability 1 by 4. So multiply with 2 into, then 1 by 4 is a probability and code word length is 2. Okay. Plus likewise we can put 2 into 1 by 8 into 3. 3 is the code word length and 4 is into, because 4 symbols have 1 by 16 probability. So the same probability, the last 4 symbols have the same probability 1 by 16. So 4 into 1 by 16 into 4. So finally we got 2.75 bits per symbol. This is the average code word length. Okay. Then find the efficiency. Eta it is equal to entropy divided by average code word length H cap. Okay. So it is equal to, because here see that the average information, that means entropy and the average code word length both are same. It's 2.75 bits per symbol. Here also 2.75 bits per symbol. So it is equal to 2.75 divided by 2.75, nearly it is equal to 1. So we got 100% efficiency in this source. Okay. Then redundancy also 100% efficiency means definitely the redundancy it is 0. Okay. Then finally, we are going to compare the Huffman coding and Shannon-Fenno coding. So in Huffman coding, it is invented in the year 1952 and Shannon-Fenno coding is 1949. Huffman coding have good efficiency and Shannon-Fenno coding has moderate efficiency. And Huffman coding was developed by David Huffman and Shannon-Fenno coding is developed by Shannon and Robert Fenno. And Huffman coding provides high optimization and Shannon-Fenno coding provides low optimization. And Huffman coding it is based on the source symbol probabilities and Shannon-Fenno coding based on the cumulative distribution function. Okay. So finally, we compare to Huffman coding, compare the Shannon-Fenno coding to Huffman coding. The best one is Huffman coding because it is a good efficiency and high optimization. It provides good efficiency and high optimization. Okay. Thank you.